Welcome to my second video, or the voltage controlled oscillator part 2. I have since made a bunch of modifications. I don't know if you could notice it in the original video, but the frequency range of the oscillator was kind of limited. You could kind of make it go, it had like a range of maybe like 100 hertz tops, which is not really what you want for any type of musical purpose. So I've made some changes to the circuitry. Mostly I've changed the values for most of these resistors. I may have introduced a couple more, but we'll get to that when we look at the schematic. I also added some diode for protecting against reverse polarity, because when you look at these plugs, that you plug one of these into, there is a moment where you can actually short, or where the tip actually hits the shield as you plug these guys in. So for control voltage, that could potentially be bad. So I added in a diode there, and then I did the same for the input voltage. And I added some tuning. With the potentiometer here, I added the LED on the CV input, so that it will actually show you what the input is. And remember, the control voltage goes up to like 30 volts or so. So I had to add a little bit of a voltage divider with two resistors, so that we don't blow up the LED here at max voltage. And then I also sharpened the waveform a little bit by adding an extra output stage. So there's two extra transistors here for the output. I also got some new power supplies, because the original one that I was using, as I might have alluded to in the original video, was kind of crap. I mean, it's good, it serves its purpose. It's just, I don't know, I think I got it for like $10 off of eBay. I think it was something like that. It was like ridiculously cheap. So yeah, I went shopping for a new power supply with multiple outputs. So now I have 4 power supplies. Thank you, eBay. Which is cool. So yeah, maybe there they are. So maybe I can add a review of power supplies. So this one here is the original one. Then I also got this one off of Amazon. And then these two are eBay auctions that I happen to have won both at the same time. I didn't expect to. But yeah, this one is cool because it's programmable. So, you type in the hard digits as opposed to, sort of guessing where you're turning. So, I don't want to go over 5 volts and half an amp, and you just type that in and it will do that. It also has remote sensing, which basically means that you can have a lead all the way back to your circuit board, and because those leads don't carry any current, they actually have a better chance at measuring back the voltage back to the power supply, and then the power supply will adjust itself to make sure that the supplied voltage and or current is at whatever you programmed in. So there's that. And then the top one here is actually also BK Precision. Those are both the same brand, but this one is a much older vintage, and it's just a regular turning knob. It's got 3 outputs. 2 are variable, and the third one is fixed at 5 volts. The other 2 have well, actually, this one I think also has 3. There's an extra fixed 5 volt one on the back. This one has connectors on the back, if you want to do some type of permanent installation. And this one, the bottom one here, is also a fixed 5 volter here on the right, and 2 variables. So lots of knobs now to play with, which is good because now we can actually have our full range of control voltage to experiment with. The downside of the fancy one here in the middle is that it's got a lot of fan noise. So it's got a cooling fan inside, and it doesn't actually ever shut off. So I'll demonstrate. It's quite loud. I mean, it's louder than any of my computers here, and I've got a lot of old computers, so I don't know, that's something. This older one here is pretty cool, just because of the analog readout. And the light bulb still works. I was quite surprised to find out that the light bulb still works. Those things usually burn out, so that's cool. I like that one. I like the feel of the knob. Anyway, so yeah, let's power this junk up. So for the regular supply voltage, so I changed the circuit so that it will work with a fairly wide range of input voltages, which is cool. In fact, I even managed to run it off of a 1.5 volt battery, just a single battery, which you can do. It's not ideal because the range is kind of limited when you do that, but possible. So hey, the regular supply voltage can be between 1.5, although I wouldn't recommend going that low, and all the way up to about 6.7 volts is where stuff starts to heat up. So I wouldn't go over that. Let's I would just avoid going over 6.5 really. It would sit comfortable at like 3 volts or even 6 or 5 or 4. So anywhere in that range is good. So and I also have this little ground bar here that I put together because otherwise I had like 5,000 clips all hooked into each other. Oh yeah, I cleaned this up a bit, so rather than using the regular jumpers, I cut a few bits of wire up to the right size so that you can see a little bit better what's going on. So yeah, that's another thing that I did. So let me hook up power here. Get this, and then our supply voltage go in here, just like that. And then our control voltage, let's use the cool vintage power supply for that one. So I'm using the bottom one for the regular supply voltage, and I'll use the little vintage guy for control. There, it's all hooked up. Let's power up the, oh yeah, I should power up the scope so we can see our output. Scope takes a while to start up. I could use the analog scope over there, but it's a little bit bulkier. Alright. Ooh. Yeah, so there was smoke because my voltage was still set to 30 volts. This is why you should not connect your leads before turning on your power supply. I did. Oh well. Maybe it's still good. It was only for a split second. All right, let's try this. Let's add some. Oh, this guy's still at 19 volts for some reason. Let's turn that down. Giving it some volts. Giving it some volts. All right. Looks good. And then turn on the control voltage. Oh, look at that. See, even though it's smoked, it still works. That's what you get with your old discrete components. Stuff is built like a tank. Shit don't break. So, alright, so here we see our two output waveforms. And when I stretch this out a little bit, you can see that the output is now a lot more square than it was before. And that is because of those two extra output transistors. So yeah, there you have it. And you can see your little LED. It's quite amazing that nothing blew up after giving it like a full 2 amps, 30 volts input and smoke. Oh, that's cool. So yeah, so we know it's robust. All right, so now let's play with the input control voltage. So that would be this guy. We're gonna meter our volts, and we can see that we're all the way up to the max. So that guy doesn't go up to 30 volts. It's only like 25 or so, but you can see we're just short of 2 kilohertz there. So that's decent. And then when I turn that down, we should be able to bring it all the way down. 300, 200, 170, and I gotta unstretch that. So it looks like we're bottoming out here at about 80 hertz. Now we can bring that down further if we muck with the supply voltage. So center this out. So now we're at 55, 53 hertz. I'm looking at the corner here, which measures the frequency, which is the main reason why I'm using this scope over the other one, because it actually has a nice, easy frequency readout. So yeah, at about 2.5 volts supply voltage, and about the same in control voltage, we're getting our bottom frequency here at about 67. I can get it to 50 something, but yeah, which is reasonable enough. And then we top out at like 2 kilohertz or so. So that's a much better range than what we had before, which is nice. Alright, so what does this actually sound like? Let me turn on the amp. Oh my god. My ears! But yeah, you can see I can lower the input, the regular supply voltage, which takes it down that extra notch in the low end. So now we're at about 1.5 volts, which is what you would get if you ran off a battery. But if you did that, you wouldn't be able to go very high in frequency, because, well, actually, I take that back. yeah, it cuts out right about there. And if you were to go higher, you'd be able to go a little bit higher in frequency. But, you know. Now I can go all the way up. I can turn the knob all the way up without it cutting out. Alright, enough of that. So, that's cool. So now how do we take that and, you know, make it into an actual little board that we can get a PCB populated for and then eventually make our module. So next, oh my god, the focus on this phone is all over the place. Piece of shit. Okay. Anyway, so yeah, next we'll go to the computer here and try to put together a little schematic and you know, a PCB board, and then we'll order that PCB board, and then you know, we'll have a more real thing. So all right, so for this I'm going to use kicad, which is this little CAD thing that lets you design schematics, simulate them with Spice, and do some PCB design. That, you know, one of the few things that actually work on Linux and are feature complete enough. So I already kind of did this because I had a few different iterations of this, but this is basically the schematic that I ended up with after, you know, experimenting on the breadboard. So here in the middle you can see the regular astable multi-vibrator thing. Fairly typical configuration, and then here on the control voltage input you've got that diode and the tuning potentiometer with the LED, and then the supply voltage also with its diode, and then here you've got your two extra transistors for sharpening and amplifying that output, which makes the waveform a little bit nicer, sharper, which may or may not be desired. But the main reason why I added these guys is because when you go and connect stuff to the output, like, yeah, we've got this here, this one, this and this isolation capacitor here, coupling capacitor, which basically removes any DC offsets that we might have on the output here, because there would be some, and basically sort of isolates the output from our circuit in order to really prevent anything that we hook up to this from affecting our oscillator circuit. These extra output stages sort of help with that as well. So in addition to making the outputs crisper, they also help with the isolation part of it. So yeah, it's super simple. It's not as simple as the cut the middle leg of the transistor thing that is floating around YouTube. Look Mom No Computer did some awesome videos on that. But it should be a bit more reliable than that circuit. Anywho, so here's that. So then I made a PCB layout for this, which we can see here. So, you know, 2 layers, you know, pretty basic. So basically, when you design your schematic, in KiCad, you can then import your schematic, and you can click that button there that says update PCB from schematic. And it'll just populate your board with components. It won't automatically be laid out. In fact, it will be a mess. And you know, it does have some auto routing features once you put all of the components in the right place where you want them on the board, but it doesn't quite do it super nicely, so you usually end up having to do a bunch of manual stuff anyway. But yeah, a quick rundown of this. Here on the right, you've got your layers. So right now we've got the front copper layer selected. This here is the back copper layer. So those are the most relevant things. Then you've got your silkscreen layers. So that's your actual printed text on the board. So we've only got a front silkscreen here. I didn't put anything on the back silkscreen. Actually, yeah, no, I didn't put anything on the back silkscreen. You've got your solder mask, and then I didn't use any of the other layers except for the edge cuts, which basically defines the outline of the board. And that's all that's on there. But with edge cuts, you can basically, you know, if you draw polygons on there, it'll basically be cut out of the board, so you can define extra cuts on there or extra holes or anything like that. Can go on there. And if we want to know what this would look like if we were to actually print it, this should have a 3D viewer. Here it is. Fancy schmancy. Now these components are not exactly right because I didn't bother selecting the exact models for most of these components, because that's a pain in the ass to do, but I got it close enough to the point where, you know, the spacing of the holes and stuff should be about right. So, you know, your capacitors won't exactly look like this, and the resistors definitely won't look like this, but you know, as long as the holes are in the right place, that's for this purpose all we care about. But yeah, there we go. So I actually went and got this ordered, and I just got a package in from China with the printed boards. So if you actually want to get this printed, you're going to want to go to plot here, and then you want to plot this, and you also want to generate drill files for this, which is going to create a bunch of files. Let's see. YouTube video. It's going to create your Gerber files and your drill files. So GBR files and DRL files, and you basically want to throw all of those in a single zip file, which I already did here. And then that zip file you can upload to the PCB manufacturer, and then they'll send you a board. So next we'll look at the board and we'll populate it, and then hopefully it will work and not go up in smoke like the breadboard did.